example. Okay. All right. So Math 300, Introduction to Higher Mathematics. Okay. What does it mean? It's primarily proofs and everything that surrounds them, but really, if you look at any kind of mathematical, more advanced mathematical book, and in fact, any calculus book, you've seen it. It's the definition, theorem, proof. So that's a format that is very tough to handle. Actually, if you have had experience with it, that's why we are starting here. So you might be reading something, there are no pictures, there are no really explanations. It is very terse, and then you have to be able to handle it, understand proofs, understand how the whole format works. You do see that in calculus book, right? So you remember, so you define your relative, and then you make a statement about the relative, and then you prove. Okay, so that's pretty much what you see in calculus. We don't want to rely on calculus too much because proofs are tough, and there's really no trick of finding proofs other than by knowing the material real well. Okay, so we try to look at the proofs in a kind of a more general way. So we'll draw from things from your earlier than calculus experience. Okay. To provide examples of this. So number one, I have an example of a proof that I want to talk about, but maybe somebody can suggest the proof for us to consider. So what is the easiest proof that you remember from high school? Any proof. And you have to with something, right? Well, it is. Somebody will beat you. We're looking for the simplest possible, so there must be something simpler than anything about relatives. But it's certainly a fair example. And some of the proofs are simple, but you need to know calculus. So before calculus. What? Okay, still. And those are pretty hard, actually. Those proofs that some of the limits are pretty hard. Now, even if you're doing epsilon and delta, it's not easy. Geometry?
Yeah, geometry.
Okay. What? Pythagorean theorem. Okay, that's Pythagorean. Pythagorean theorem. That's a good one. Okay, so anything simpler than that? Well, first of all, anybody remembers how to prove it? Well, so what you probably can think of is something simpler than that. Okay, well, in geometry for 1, there are simpler, for example, well, here's an example. The sum of angles is 180 degrees. That's a simpler statement, and it is simpler to prove. Well, it's more for fun, I think. Angles of a triangle is 180 degrees. Okay, so that's another one. But geometry does require, you might remember the Euclidean geometry actually is based on Euclidean axioms. And so that's exactly what we have over there. Well, exactly, actually, one missing part here is that you might face this. Not just definition and theorem and proof, but actually start with axioms, and then you derive things from those axioms. Okay, so then Euclidean geometry is based on Euclidean axioms, and there is a challenge there because there's a bunch of them, and you have to develop theory very carefully at the simplest to more complex. And this is, by the way, I do believe that a lot of the Pythagorean theorem proofs require results such as the last one. So the point is that there are algebra results that are simpler. And you probably don't think of them because they are seem so obvious. So let me just tell you what I have in mind on putting in the form of a theorem. The sum of two even numbers. What? What? Even. Is even, yes. The sum of two even numbers is even. Okay, so that's it. So that's what the good thing about algebra. We don't really need any actions. We can assume that we know algebra and what algebra is about. There are a bunch of proofs that are fairly short, and we can make a point of how to deal with that. So how to handle proofs. So first of all, is it obvious result? So obviously, I mean, you can try a bunch of numbers and you can discover that fact very easily. 2 plus 4 is equal to 6, and just by examination you will notice that pattern. So now it is a pattern how we discover results, but then how we prove it matters. We have to be very careful. Well, how do you start? Typically you don't start writing the proof if you have never seen it before. You start with analysis. Analysis, so that what you have to bring to the table in order to write out the proof. So what do we need to bring to the table? Well, look at the list again. What?
What an even number is.
That's right. So this is the key step is here. You cannot really start putting anything unless the definition is available. Here, how many times do we have to use the definition? Okay, let's define first. So an even number, what is an even number? What number do we call even?
It's divisible by 2.
Divisible by 2. If x is divisible by 2, okay, which is fine. As it often happens, you might have to elaborate in the sense that we do know what even number is, but we define it in terms of a number being divisible by another number, which means that you have to explain now what divisible means. Divisible by 2. So we need to define. You see, if you just make a statement about numbers 2 and 4, and you say, well, 2 is divisible by 2, 4 is divisible by 2, 6 is divisible by 2, all fine. But if you want to prove this kind of statement, which takes care of infinitely many numbers at the same time, okay, so you have to be very specific about what words that you use, what they mean. So divisible by 2, what does it mean exactly? Yep. You don't have to write it again. Just.
Is that true? Because I thought 0 was neither even nor odd.
I know there is a controversy about that, but I wouldn't worry about it. So 0 is also even. So what does it mean? Divisible by 2. What do they have in common? These three. Yeah.
2 is the factor.
What?
2 is the factor.
2 is the factor. That's one way to put it. Okay. 2x has 2 as a factor. Okay. Then you have to explain the factor. Okay. And then the factor is the number by which x is divisible. So we're back to that. Well, that's okay. You look at it, it's analysis. So we're just analyzing things, and we try to get to the bottom of it. But it's not a useless observation, because actually it takes us one step closer to what we are looking for. And the starting point is x is an integer. it is assumed, obviously, if you're talking about even or odd, you are not talking about fractions, you are not talking about pi, you're talking about integers. Okay, so that limits our attention to a smaller collection of numbers, like this, -2, -1, 0, 1, 2, 3. Okay, you can actually look at this and just mark the numbers that we're interested in. So, even. Okay, so they seem to be skipping one, and the rest of them are called odd. So, okay, so it is an integer to begin with. Okay, and secondly is divisible by 2. In other words, 2 is a factor, or simply this is how I take this and rewrite it: x is equal to 2y, where y is another integer. That qualifies as a definition of an even number now. So this is the good thing is that we're not talking about division, we're not talking about factors. So there are no new numbers, no new concept brought into this unnecessarily. So all we're talking about is multiplication, and we're talking about the other integer. That's all. So this is the way to define even numbers in a like this, and like this. If you want to do anything with them. So there are many interpretations or facets of this idea, but really, if you want to have a definition, you want to write a proof, this is the way to go. Okay, so it is, as you can see, you can still see that x is divided by 2, because if you divide x by 2, you have y. Firstly, 2 is also a factor. Okay, we can see that too. And yes, we don't have to talk about neither factors nor division. We can just have this as the starting point. So that's our definition. So on that list of things that we have, I only marked 3 because axioms, as I said, for the time being, we'll try to keep them away from us until later. So we'll just stick to things that are, even though they're defined, they're not based on anything more than just a few lines of the definition. So that's one line of the definition. X is called an even number if x is equal to y for some integer y. Okay, so now this the whole theorem is entirely about this and nothing else, right? So this is my theorem, and okay, so as a question I asked, how many times we're going to use this definition? What?
At least once.
Yeah, well, obviously, if it is less than once, then we'll probably be wasting our time. We use as many times as numbers we have. How many numbers do we have here?
So,
And the sum, that's the third. It is actually we're going to use it 3 times. So as you can see, that's a useful discovery that we made about the definition, because we're going to use it 3 times. A very, very simple statement, we have to use that definition 3 times. So x is equal to y, where y is not integer, is what we have here. Okay, so all right, so we're going to have 2 integers, and then when you do the proofs, you're probably going to use letters. Sometimes it's very nice to write here with no letters whatsoever. Just say in words. It's easy to remember. It just flows off your tongue. But really, once you get to the proof, you want to introduce letters. So we suppose that we have two integers, two even integers, and you call them, say, A and B. So you give them names. Okay, and then what? And then you use the definition. So let's go one by one. So A is even. So by definition, what does it mean? Pick a letter, 2 times, and then, which letter? I don't want to use y because it's in the definition already, and we're going to use this definition. We're going to apply this definition to every number that we already have. So how about n? Okay? N is an integer. Okay? B is zero. So by definition, b is equal to 2 times, once again, you pick a letter that you like, but not, you're using the definition that in orange over there, and so we have letter x and y, but we have changed x to b, to a, and then to b, so we are very carefully not to recycle letters that are used in the definition itself, otherwise we'll be messing with our heads. We want to do it carefully so that we write it out and then we're done with it. There will be nothing self-referential or circular. Okay, so m is an integer. So we have taken care of what? We have taken care of the setup of the theorem, meaning the conditions of the theorem, and then we draw a conclusion. So in fact, probably another way to rewrite our theorem, let me rewrite the theorem, and now as we have started, so rewritten. All theorems, we're going to talk about that a lot. All theorems, all statements of mathematics were sort of two, or they are if-then statements. There's a condition, first if, then condition, then conclusion. Okay, so if, then. Okay, so the theorem is the same. The sum of two of the numbers is even. Okay, so what's the condition of the theorem? Or hypothesis is another one. Right. Yeah.
If you sum two equal numbers, then they're equal.
Right. So then they're equal. They're even. The sum is equal. So let me use the letters we already have. A and B are even. Then A plus B is even. Okay. So I also want to have this notation that is commonly used and make things slightly shorter. So say A, B are even. Hypothesis or condition. Then is often replaced with this symbol. A plus B is even. Okay. So then the starting point, and then somehow through logical steps in algebra we have to arrive to the last one. Okay. The first one has been taken care of. We already know exactly what it means. Okay. So then before we start writing any kind of proofs, we can ask ourselves what is the conclusion says, and what does it say? The conclusion says it's even, so how do we put it? So A plus B is even. The definition at the top.
So A plus B equals 2K.
2K. Very nice. K integer. Okay, so that's what we are trying to arrive to. We haven't established that, but we now clearly outline the beginning and the end of our journey. And so the beginning of the journey is, in fact, right here, and this is the end of the journey. Oops, right here. Okay, so that's we have to make that trip. We haven't even tried to prove anything. What we have done, we were able to get rid of the words. So we made it purely algebraic without using the word even though the theorem is about even, but you have to unwrap that word, which contains a lot of information, but when you prove it, you have to actually get rid of it, because unless you have other theories to use. So for example, if we talk about triangles, right triangles, you can always use the Pythagorean theorem, and you don't have to actually define what right triangle means. But here we are not going to be using anything, just algebra. So just as well, we were able to get rid of all the words. So the word even is gone. So I circled the pink over there. A is equal to 2n as an integer, b is equal to m is an integer, and now we want to demonstrate that a plus b is equal to k is an integer. I hope you already see what we do next. So how? What do we do?
Substitute.
Yes. So where?
For A plus B equals K.
That's right. So
Substitute.
A plus B, we introduce two new integers. A and B were given, right, on the left. We introduce two more integers, n and m. Okay, so now we want to get rid of a and b so that they wouldn't be in the way, because we're now talking about the sum. So it will be 2n plus 2m. Okay, and once again we are keeping an eye on our goal. It's on the right. Okay, so it's a plus b is supposed to be equal to 2k, and so far it is equal to n plus 2m. Okay, so what do we do?
Equal to 2K.
I guess I don't really. Yeah, it's fair. It's fair. 2K. Okay, so 7 equal 2. Just we are not saying that they are, but we because otherwise we cannot assume that they are because that's what we're trying to prove. Okay, but we can set it up equal to each other, so we're still doing analysis, and that way we can figure out. After all, we're supposed to find K. Right, so another way to demonstrate that A plus B is even, they just simply find K, and I think we're just almost found it, right? So for K, and so we have, what do we get? So this becomes an equation, right? N and M are just two integers. A K is an integer also, what we need to find. Okay, so let's find it. If it is impossible, we'll discover that that equation has no solution. Okay, but fortunately, well, we can solve it. So, what is K? N plus 2m is equal to 2k. What is k equal to? N plus n. So k is equal to n plus n. We just divide by. Okay, so the other thing that remains is to make sure that the condition is satisfied, the conclusion is satisfied. So even though we do have a plus b is equal to k, what remains to be shown is that k is an integer. Of course, it is an integer, so we have to. I don't want to go into the axioms of integers, but let me put it this way: is an integer as a sum of two integers. So we have to, you can try to back up your statements, and then every statement might require a new backup. Okay, so you just have to be reasonable not to go too far, and then, for example, we don't want to prove that the sum of two integers is also an integer. Let's suppose we already know that from elsewhere. So, and as long as you stated explicitly that I am assuming or concluding that k is an integer because it's the sum of two integers, and then we know that the sum of two integers is an integer. Okay, so and then you're done. Okay, so we're done. Okay, so it seems that we have discovered a proof. We haven't written a proof, so this is still has been analysis, which means that we have all the pieces of the proof here. We just have to put them together in the right order. Okay, frequently analysis is in the wrong order. You may have seen that in calculus sometimes, some calculus that. Or maybe solving equations. Have you noticed equations or inequalities you're solving, but that really is not a solution as much as if you retrace the steps and you go backwards, that's a solution. So you are discovering the solution in one order and then prove and then prove that it is indeed what you claim to be in the opposite order. Okay, so let's quickly write the proof. Based on this, pretty much just these pieces will have to reappear. Okay, let me start over. We'll do it from memory. Okay, so here, once again, the sum of two even numbers. This is even proof. Okay, so introducing letters. So starting from nothing, suppose what was it? A and B, A and B, R, B, R, B, are the integers. Okay, since A is even, A is equal to 2n for some integer n. By the way, they could be negative. Now, B is even, so I'm writing what we would have. B is equal to n for some integer, yeah. Okay, so now consider A plus B. A plus B is equal to 2n plus 2m. Okay, at this point I could do the way we did it, or I could just say streamline it a little bit. I just factor 2, n plus m. Okay, where n plus m is an integer as the sum of two integers. So A plus B is given. And okay? So that's roughly what it is supposed to look like. Our proof, that is fairly straightforward once you write it out. But what we're doing in this course is really not studying algebra, we're not studying calculus for sure, but we're trying to learn how to handle proofs and writing them as we did, but we also will look into proofs and trying to make sense of them, because some of the proofs are just very terse, and they skip steps, and then you have to fill them out, and then also you should be able to, that's a big deal, criticize your own proof. Okay, so you will try to criticize other proofs, but it is ultimately your responsibility to make sure that your proof is correct, and some logical flaws in the proofs that you should be able to discover at some point. Okay. Okay. Well, before we move on, there is more to this proof, and you don't want to. That's a good proof. Okay. So what we could try to do is to recycle it and maybe get more from it. Can you see how we can get more results from it? Remember the divisibility idea of interpreting even numbers as divisible by 2? What if it's divisible by 4? So once again, a number is even when it is divisible by 2, period. Okay? But ultimately, we know what it means. It's simply we can write an even number as over there a is equal to 2n, or I'm sorry, this is supposed to be. Okay, so what if I have a 3 here? So rather than speak of a is even, how about it's divisible by 4? So how does it work out? Well, let's go over it. So we have two numbers divisible by 4, A and B, which means that they simply have a factor of 3 instead of 2. I replace each 2 with 3. Okay? So, and n and m are still integers, and then I proceed to that line over here, 3 and 3, and then what do I do? I factor 3 out of it. Okay? So what's the conclusion?
The sum of two multiples of 3 would be...
That's right. The sum of
two numbers
divisible, yeah, it's let's sound a little bit better. Two numbers divisible by 3. By 3 is divisible by 3. Okay? Is anything special about 2 and 3? So. Okay, so let's use it more. So what else can we get from this? Divisible by 2, divisible by 3, any number. Yeah, that's right. I could put any number I want over here. I don't know, p. So we have two numbers divisible by p. We add them together. The result is also divisible by p. Okay, so it doesn't matter what that number is. It could be prime or not prime. It doesn't matter. The proof works out. Every time I do it, just every 2 is replaced with p and we're done. Okay, so the proof remains intact. So that's what happens when you write proof properly, and you don't rely on your intuition about the meaning of the numbers, even examples of the even numbers. You just tweak it a little bit, and you get way more from this theory. For the proof more than from the theory, right? So you cannot really, once you're done over here, if you just keep in mind only the theory, then you might never discover the generalization of this theory if you omit the proof. It is the proof that contains all of those results in potentially, and you just have to work it out. Okay, so what we're going to be doing here is I don't want to forget this big deal over here. This one about if then interpretation of everything that you say in mathematics. Okay, and because we're going to tweak these and making conclusions about something more complicated than just two numbers. For example, how about we have 3 numbers? 3 even numbers added together give you again an even number. Why? Look at the proof. Instead of a plus b, it will be equal to plus c, and once again you factor 2 out, and you have once again 2 as a factor of the sum. So you can produce all kinds of results in this fashion. But what I wanna look at is other if-then statements and how we have to be careful with those. So if then statements. All of the statements are if-then statements. If there is no if-then, then there is probably there might be something missing. So I don't know. For example, at its simplest, if x is equal to 2, then x plus 2 is equal to 4. Okay, so that's the simplest if-then statement. Okay, by the way, every time you're solving an equation, this is there's a link here that I want you to follow. That is course policy, and so it actually, I forgot to mention it explains things in more detail. Okay, even though it applies to different courses to a different degree, and this is what I meant, and number 6, writing, and the computations have to have equal sign in them. Okay, so unfortunately I have seen too many times when equal sign is omitted and the computations go as 1 plus 1, 2. So that's a mistake that we are sort of past already because we're not going to be doing a lot of computation, we're going to be doing proof. So the next line is important. It is when you're solving equations already kind of doing a sequence of steps, and then you are just not connecting those statements to each other. So over there, 2x plus 4, 2x is equal to 4, therefore x is equal to 2. So we write the proof, so there will be a lot of words that connecting our statements, as we just done. In this example. Minutes left. Let me see what we can do with statements like that. So let me pick another statement. Okay, here it is. Here's the statement. Statement A. Statement A. Okay, every student in this room is an economics major. Okay, so let's make it if then statement.
If a student,
What's the condition? Yeah?
if they're a student in this room,
No.
If the student says they're an economics major.
No.
if the student is in this room,
Yes.
they are an economics major.
That's right. Yeah. So if a student, so that's what happens to every, any, and all of those words. They turn into one particular, they turn into a condition. So if a student is in this room, he or she is, then, okay, let's not forget, then he is an economics major. Okay, so once again, if, then. The converse, anyone? And remember what converse is?
If they're not in this room, they're not an economics major. Opposite.
Now that's the opposite. The converse is you reverse the arrow from this direction to that direction.
If the student is an economics major, then he is in.
If the student is not an economics major, he's not. Yes. Okay, we'll talk about that next time. Thank you.